friends to our PCS-IBS seminar. Today, we have a pleasure of hosting Dr. Leonardo Zambrano from the Institute of Photonic Sciences. Leonardo is a postdoc in the group of Professor Antonio Sin in the ICFO. And today he will talk about variational quantum algorithms for the geometric measure of entanglement. Leonardo, the screen is all yours, please.
Thank you. Good morning, everybody. Thank you for the invitation and the kind introduction. I'm really glad to be here. So today I'm going to talk about some work that I've been doing with some collaborators, and it's about variational quantum algorithms for the geometric measure of entanglement. So we want to estimate this geometric measure of entanglement in an effective way using variational quantum algorithms. And for that, we have to avoid one of the problems that VQAs have, that is the barren plateau phenomenon. So in this presentation, first I'm going to talk a bit about variational quantum algorithms in a general way, basically what these methods are. Then I'm going to pass to the barren plateau phenomenon. That is a big problem that the variational quantum algorithms have, and that makes many of these VQAs not very useful yet. And finally, I'm going to describe a proposal to avoid the barren plateau in the specific problem of estimating the geometric measure of entanglement for pure states. Okay, so variational quantum algorithms are one of the most promising strategies to obtain quantum advantage using noisy quantum devices. And here we want to solve useful problems using parameterized quantum circuits together with classical optimization. So this is an analog of the classical machine learning methods, so because we have an architecture that in this case is quantum, a bunch of parameters that are classical but control the quantum circuit. And we want to update those parameters to learn a good model, a good solution for the problem. So VQAs usually have three elements. The first one is the parameterized quantum circuit, or ansatz, that is usually composed of layers of quantum gates, where each one of these gates depends on classical parameters. So by changing these parameters, we can explore the Hilbert space and then encode the information of the problem in the quantum computer. Then there is the cost function that represents the problem that we want to solve, and it's the function that we want to optimize using this quantum circuit. For example, in a chemistry application, the cost function could be defined as the energy of the molecule. So this would be the expectation value of the Hamiltonian response. And then the goal would be to find the state that minimizes this energy. Okay, but in any case, in any cost function, we have to evaluate these functions. We have to take some measurements from this quantum computer and post-process those measurements classically. And finally, we need an optimization algorithm that, given some evaluations of this cost function, adjust the parameters of this quantum circuit to optimize the cost function. And for that, we can use gradient descent, or actually almost any classical optimization technique. So these are basically the three main elements in a variational quantum algorithm. We have the ansatz, the cost function, and the optimization algorithm. Okay, so now these are the steps in a variational quantum algorithm. So here, first we have the initialization, and here we choose some classical parameters and we prepare the ansatz, the parameterized quantum circuit, with these initial values. And those initial values can be random or not, depending on if we have some previous information of the solution of the problem. For example, if we want to find the ground state of a molecular Hamiltonian, we know that usually the Hartree-Fock solution, that is something classical and efficient to calculate, is close to the solution that we are looking for, and then we can prepare the ansatz in the Hartree-Fock state, for example. So, but in this step, we just have to choose these the initial parameters that control our quantum circuit. Okay, so in the second step, we have a quantum circuit that depends on classical parameters that we have chosen in some form, and then we run this quantum circuit on a quantum computer to generate a quantum state. Then we measure some expectation values of observables to obtain the information about the state. And here the relevant observables could be the Pauli strings that form some Hamiltonian, for example. Something important here is that to estimate this expectation value of observables, we have to prepare and evaluate this circuit many times. But in general, this second step is just prepare and measure this quantum circuit with some observable many times. Then, once we have this information, the next step is the gradient calculation of this cost function with respect to the classical parameters that control the quantum circuit. And for that, we use the data that we obtained in the previous step. And well, here the gradient indicates the direction and the magnitude of the parameters in the next step. Like is the direction of the movement in the next step. And this is what we need to update these classical parameters that control the quantum circuit. But this is something classical. This is something that we do on a classical computer. And the gradient is just an estimation. It's stochastic. We only get an approximation of this gradient. So once we have the gradient, the parameters are updated using some specific optimization algorithm. And here there are many methods that we can use, many different optimization algorithms. And finally, after updating these parameters, we evaluate if the optimization process has converged with some convergence criteria. For example, the parameter updates are really small. And if the convergence criteria are met, we stop the process and we output the solution. And otherwise, the process continues repeating steps 2 to 5. So this is in general a variational quantum algorithm. We optimize some function using the outputs of a quantum circuit, and this quantum circuit depends on some classical parameters. Good. So there are several areas in which VQAs are promising and might provide an advantage over classical algorithms. The first one is quantum chemistry, because we are using a quantum system to simulate the Hamiltonian of another quantum system. So you can use these VQAs to calculate molecular properties like ground state energy or first excited levels, etc. And in this case, you minimize this function, the expectation value of the Hamiltonian of the molecule or atom. And from the variational principle, you know that this is going to be an upper bound for the energy of the system. And this is something that is very difficult classically, because in principle, you have to represent this state here as a vector. And since the dimension of this vector grows exponentially with the number of qubits, or the number of modes in your molecule, the problem becomes infeasible very, very fast. Okay, so VQAs might also offer some advantages in solving optimization and combinatorial problems, like graph coloring and traveling salesman problems and portfolio optimization. And the advantage here is not exponential, because these are problems that are NP hard, but they might offer a polynomial speed up. So these problems are reformulated as Hamiltonian minimization, and they are mapped onto a quantum circuit, and then this kind of cost function is optimized to find the optimal solution of your problem. And well, finally, VQAs might have some potential in machine learning tasks such as classification and generative modeling and data analysis, since we have a huge Hilbert space in which we can encode our data. And in this case, the function that we have to optimize is a loss function like this. And here we have a sum over several initial states that represent the data that we are including in our algorithm. And okay, so there are also proposals for VQAs in quantum data compression, quantum error correction, quantum metrology, and actually many other areas of science. Okay, so that was basically the introduction to VQAs. And before I start talking about the barren plateau phenomenon, I have to talk about the ansatz, because they are very important for this problem. So in a variational quantum algorithm, in principle, the ansatz could be anything. We have a lot of freedom here, but there are several choices that are common in the community and that have good properties. So the first one is the hardware efficient ansatz that we see here, and the motivation of this ansatz is that we only apply gates that are native to the device. So we have single qubit gates that are rotations, and there are the gates that define the parameters of the ansatz, and after them a ladder of CNOT gates. And this is a basic block, and then we repeat this basic block many times to get this full hardware efficient ansatz. Something important here is that we only apply CNOT gates that are the most expensive gates, the more noisy ones, to neighbor qubits. So for example, here in this circuit, we could apply CNOT gates between qubits 0 and 1, 1 and 4, and 1 and 2, but not between qubits 1 and 12, for example. Okay, so yeah, but this ansatz has some limitations. And one limitation is that to make sure that we can express the solution of the problem, the ground state of a physical system, for example, we need to span a really large portion of the Hilbert space. And this is because we are not expressing any of our previous knowledge about the problem in the ansatz. For example, if you have a molecule, you know that molecule has some symmetries, and you can use them to reduce the complexity of the problem, but not in this case, or well, at least not in this basic formulation of the hardware efficiency. So what you have to do is to create this ansatz, add many layers, and hope that the solution of your problem is inside the span of this ansatz. And that, in some cases, might need a circuit with exponential depth and lots of parameters. Okay, so a different ansatz is this unitary couplet cluster, UCC ansatz. And this is an ansatz that is chemically inspired. So we have this Hartree-Fock solution that is classical and easy to calculate, but it doesn't capture the electron correlation. And then we have to modify this state, improve it a bit using this unitary. So electrons are fermions, and they can occupy orbitals and of molecules and atoms. And this operator takes one electron from one orbital and moves it to another one, and this other operator takes two electrons and moves these two electrons to other two orbitals. So in a simplified form, this unitary coupling cluster ansatz applies the exponential of t, this operator t, controlled by this theta, these classical parameters, to the classical solution. So with this, we get a big contribution of the, see, yeah?
Is the ansatz good on the hardware? Because, I mean, let's say the creation and the annihilation operators, when expressed in terms of the qubits, they are very non-local. So is it doable to apply this algorithm on an actual quantum device?
Yeah, in current quantum devices, it's not very good. Well, here you have these classical parameters, and in principle, you have less classical parameters than in the hardware efficient ansatz,
right?
Because you are using some previous information about the problem. You know that the solution is going to be close to this Hartree-Fock solution.
Yeah, but also, yeah, that was the second question. I mean, the Hartree-Fock solution is because you have to prepare it as a quantum state. So you have to implement the gates that do that Hartree-Fock solution. Is it cheap?
Yeah, yeah, it's not very difficult because the Hartree-Fock solution is just you have n electrons, so you have it's a separable state. The Hartree-Fock solution.
Is it separable also in the spin basis? I mean, I understand that it's separable in the electronic basis, but also in the spin.
Yeah, if you use the Jordan-Wigner mapping, for example, the solution is a separable state. So you have this annihilation and creation operations, and you have to map them to the qubit operators, right? Polysters.
But the map will be highly non-local, so that's why I'm perplexed that it remains separable and so on.
Yes, so the Hartree-Fock state is a separable state, but this might be non-local. Yeah, the operators might be non-local. And also, in principle, with the UCC ansatz, you have less parameters, but you have to apply sometimes CNOT gates between qubits 1 and 23, for example. And then you have a big overhead because you have to decompose that CNOT gate into into CNOTs in this path, right? So the depth might be larger than the hardware efficient ansatz. So yeah, it's not hardware efficient in some sense. And we don't like that. Yeah. But at least you are using some information. You know that the solution is going to be close to this Hartree-Fock state. And in the case of the barren plateau phenomenon, this might be better. Maybe in the future when quantum computers are not so noisy as now. Okay. Should I continue? Okay. So these are two ansatz, but there are many other ansatz like adapt VQE, Hamiltonian variational ansatz, qubit coupling cluster, and so on. And also there are different versions of each one of these ansatz. So it's a large field inside this VQA. Good. Now I want to talk a bit about the expressibility of the different ansatz. So when we choose an ansatz, we want to maximize the overlap with the part of the Hilbert space that contains the solution, because we want to be able to approximate the state that is the solution of the problem. And then we want an expressible ansatz, but the problem is that highly expressible ansatz could be very hard to train. So an ansatz is really a family of unitary transformations U, and this family has some probability distribution associated. So they depend on classical parameters, and then we can sample classical parameters and get a distribution for this unitary C. Then you can quantify the expressibility of the ansatz by calculating the distance between the distribution of unitaries that you can generate with the ansatz here on the left, on the right, yeah, on the right here, and the uniform distribution of unitaries. And in this case, we consider the distance to t moments. So this, in some sense, how far you are of being a T design. And why are we using the uniform distribution? Because in principle, this is the most expressible distribution possible, meaning that it covers all the states in the Hilbert space with equal probability. So once we have this superoperator A, we act with this superoperator over the initial state and the Hamiltonian. We calculate the norm, and if the norm is 0, the ansatz is maximally expressive for our VQA application. Yeah, so this is basically how far we are of being a two design with our ansatz, or a T design in principle. Okay, so now I'm going to talk about why these variational quantum algorithms are not very useful yet, or at least one of the reasons, and it's that they are really, really difficult to train. And it's really difficult to find the parameters of your ansatz that give you a good solution. So, yeah. And the problem is the barren plateau phenomenon, which happens when the gradients of the cost function with respect to the parameters of the quantum circuit become very close to 0 with a very high probability. So in an optimization algorithm, of course, you need the gradient to update the parameters. But if the gradient is always 0 or very close to 0, you always stay around the same point, and you will never reach the optimal solution, basically. So if you have a cost function like this and a generic ansatz like this, so layers of exponentials of Pauli's and fixed gates, CNOT gates, for example, the first fact is that in general, the expectation value of the gradient of the cost function with respect to any of these parameters theta is 0. And here we are calculating the expectation value with respect to these parameters. So the expectation value of the gradient is always 0 in general. Then to define the barren plateau phenomenon, we require that the variance of these gradients of the cost function to decay exponentially with the number of qubits, because this means that the probability distribution of the gradients is very narrow, very narrow around the mean that is 0, and then when we are at a random point, the probability of the gradient to have a big value is almost 0 using this Chebyshev inequality. And we see this in this figure because if we start our optimization algorithm here in this flat area, we will never reach the optimum because 2 points in this flat area have almost the same value. And then when you calculate the gradient, we will get 0 or something really small. Well, in this other figure, we see that the barren plateau usually happens when the number of qubits in the circuit increases. So here, different curves are different numbers of qubits. And for 14 qubit, we have a variance of 10 to the minus 7 for 300 layers. Yeah, around 300 layers of the ansatz. And this is something that we can also see in this equation. The variance decays exponentially with the number of qubits. And then the landscape, the graph of the cost function becomes flat in most points. And then if the landscape, if the graph of the cost function is flat, to see the difference between those between 2 points and calculate the gradient, you need an exponential number of shots of experiments. And then we lose all the quantum advantage because it takes an exponential number of time to measure an exponential number of shots. So this is the definition of the barren plateau. The expectation value of the gradient is 0, and the variance decays exponentially with the number of qubits. Okay, so the previous slide was a bit general, but now I'm going to talk about the causes of the barren plateau phenomenon. And the first analytical demonstration was in this paper by McLean, et al. In 2018. And they showed that the barren plateau is very related to the complexity of the ansatz. So if you have a circuit that is very complex with a large number of layers and parameters, we will have a larger probability of finding barren plateau. And this is related to the expressibility of the circuit. So if the ansatz forms a unitary to the sign, then we for sure will have a barren plateau in our VQA. And when we are talking about that to the sign, we are saying that these two terms are the same. So on the left, we have the ensemble of unitaries that can be constructed using our ansatz. And on the right, we have the uniform probability distribution over the set of unitaries, the Harmesh. So here we are saying that our ansatz, with our ansatz, we can reproduce the properties of the uniform distribution for any polynomial of degree 2. And this is the definition of a to the sign. And this is important because the variance is a polynomial of degree 2 in our ansatz. So any variance that we calculate using a unitary that forms a to the sign will give the same values that the variance calculated using the uniform distribution of unitaries. So in the case of variational algorithms, we define an ansatz of this form. So we have unitaries that depend on classical parameters and other gates that are fixed, CNOT gates. And the cost function is like this. So we want to minimize this energy. And now we assume that we want to calculate the variance of the partial derivative of the cost function with respect to some parameter k. So we write our ansatz in this form, where UL are the layers that are before this parameter k in the ansatz, and UR are the layers that are after this parameter k in the ansatz. And then the variance of this quantity of the partial derivative of the cost function is given by this expression that we see here. And the important part here is that this is a polynomial of degree 2 in the ansatz. Yeah, so this is a polynomial of degree 2 in the ansatz. So the basis of this demonstration is this to the sign property, because we now calculate the variance using over the hard distribution of unitaries, which is easy because there are some well-known formulas to do it. And since the ansatz is a to the sign, the value of the integral will be the same and exponentially decaying. So we will have a barren plateau. So is it clear? This?
Yeah.
Yeah. Okay. Very good. Okay. So the previous results can be extended to circuits that don't form a to the sign, but that they are close to one. So remember the definition of expressibility. That was this minus this, and then we take the norm and we apply this to the Hamiltonian and to the state. We have this inequality, this bound for the partial derivative of the cost function, and this is the same quantity as in the to the sign ansatz, but we have these other terms. And these other terms are very close to 0 if the ansatz is very expressive. So if the ansatz has a high expressibility, we will have a barren plateau for sure. Okay, so the barren plateau's result that we saw here is not very good for VQAs, because we want circuits that are expressible, because we want the ansatz to approximate the solution with high probability. So we want this blue area here to include the solution. But if we have too much expressibility, so we are spanning too much of the Hilbert space, we will have a barren plateau for sure. Then we have to be careful when we choose the answer, because we have to induce some bias on the problem. But we need to make sure that the solution is included in the ansatz. And yeah, so it's a bit of a trade-off between expressibility and bias that we are inducing in our ansatz. Something that is also important is that these two design properties sufficient condition, but not a necessary one. So even if we don't have a barren plateau, if we don't have a two design in our ansatz, we can have a barren plateau. So a possible solution to this kind of barren plateau, this two design kind of barren plateau, is that we have to use, of course, an ansatz that doesn't form a two design. We have to add some bias to the problem from our previous knowledge. So, for example, we should use the UCC ansatz instead of the hardware efficient one, because with the UCC ansatz we have less parameters and we are starting a bit closer to the solution. Also, if the ansatz forms a two design, we have to we need to make sure that we don't start from a random point, because if we start from a random point, the probability of being in a barren plateau is almost 1. Okay, so as I was saying, two designs are not the only source of barren plateaus, because also the choice of the cost function is very important in the appearance of these barren plateaus. And they show in this paper by Cerezo et al. These global function barren plateaus. So global functions where we compare states or operators in exponentially large Hilbert space tend to exhibit exponentially vanishing gradients. And on the other hand, local cost functions that compare objects with respect to individual qubits can have variance gradients that vanish polynomially, so they don't present barren plateaus. So this is an example of a global cost function, of a global operator, and the cost function is basically calculating the fidelity between this zero state with the state produced by the ansatz. And to estimate this function using a quantum computer, we have to measure over all the qubits at the same time. So it's a global cost function, and this function presents a barren plateau. And if we use this Hamiltonian, we have a local cost function where we only measure over one qubit at a time, and then we sum. So in this paper, the ansatz that they chose is of this form, where you have blocks of unitary gates acting on neighboring qubits. And an assumption here is that each one of these blocks should form a local two design. So a two design for two qubits. So if this happens, if each block in the circuit forms a local two design and the cost function is global, then a barren plateau occurs for all depths. Even for one layer in your circuit, you will have a barren plateau. And this is what this figure shows. So we have the global cost function that you get by measuring over all the qubits, and a barren plateau for all the depths of the circuits. And for local cost functions, they prove that you don't have a barren plateau if the depth is logarithmic in the number of qubits. So with this information, we know that we have to be careful when we choose our cost function, and that we have to choose this cost function local.
Is this result, let's say, highly dependent on the choice of the ansatz, because they want to infer something about the cost function, but for that they took an ansatz for the circuit. So is this result stable for changing the circuit or not? Or they don't say anything?
At least for the hardware efficient ansatz, this two design property is satisfied. Yeah.
But so you say to prove that you have this, let's say, trainable transition and then barren plateau, the only assumption is that they are local to design?
Yes. And that the cost function is local. So you're only measuring one qubit at a time, or two qubits, or not too many qubits. Yeah. And finally, noise can also cause barren plateaus. And in this paper, they show an upper bound on the magnitude of the gradient plateau that decays exponentially with the number of layers of the ansatz. So the gradient vanishes exponentially in the circuit depth. They also use an ansatz and a cost function of this form, but they assume a noise model like this. So after applying one layer of the ansatz, they apply this noise channel to every qubit independently, and the noise channel is simply a local Pauli operator with some probability Q. Then when we apply this noise model, the cost function is like this. And in this paper, they show that given these ansatz and the noise model, this new cost function concentrates on a fixed value. And then we can't calculate gold gradients, because to calculate the gradient, you need to compare 2 points and see if in one point the function is larger than in the other one. But if the function is exponentially concentrated, we will need an exponential number of shots to see the difference and calculate a meaningful gradient. So they have a barren plateau. And this is what we see here in this figure. We see that when we add more and more layers, the cost function starts to flatten. And the barren plateau here is different from the others, because here the result is not just probabilistic. So in the previous case, if we started at a good point, the gradient was different from 0. Here, the gradient concentrates at every point. So even if we start close to the solution, our cost function is local, and our circuit doesn't format to the sign, the gradient will be 0. And we won't be able to get any meaningful information about the problem.
But wait, but are there points in which, because here it looks in your final C,
yeah,
it looks that essentially the global minimum is as good or as bad as the local minimum. So there is no minimum. So the question is, elsewhere, do you have a true minimum? How can I say? Because in principle, if everything becomes flat, then any random point is as good as the true minimum.
Yeah.
So I wouldn't say that this is a barren plateau. I would say that this is essentially that any point solve your problem.
Yes. Yes. So this is a cost concentration. But if you want to calculate the energy of a Hamiltonian, for example, you need the value of this cost function. But all the values of your energy will be the same. So it's like a completely flat landscape.
Okay, but the true ground state is represented in this landscape or not? Because if the true state, no, okay, so you are saying that you destroy the expressibility of the ansatz.
Yeah.
Okay. No. Because if it is expressible and the plateau is everywhere flat, it means that also the true ground state energy is one of that energies. So that means that there is no problem in this plateau.
Yeah, but for example, if you have a molecule and your energy is minus 100, this flattens that energy, and you get that the minimum is minus 10 or something. So you don't get the good value of the.
Fine. So that means that your ansatz is not expressible. Or it means that elsewhere you must have a point in which the energy is minus 100.
Yeah, so you don't have that point anymore. You don't have that point.
So you're saying you are not expressible.
Yeah, you can think. Yeah, you can think like that. Yeah.
Almost related to the initialization. So with a random initialization, you see this flat pattern where.
Okay, so that means that elsewhere there will be a point with the.
Yeah, there is when I might process it, but
okay, but
you're not there yet.
Okay, okay.
Yeah. Yeah. So this is really bad because, for example, with the previous barren plateaus, the two design one, we could use, for example, UCC ansatz. And that, in some sense, was solving the barren plateau problem. But the UCC ansatz has a large depth, so you avoid the two design ansatz, but you get this. You avoid the two design barren plateau, but you get this one, that the noise-induced barren plateau. So the only solution here is to improve the hardware and use ansatz that are not deep. Yeah. Yeah. So okay. So that was the barren plateau problem. And finally, now I'm going to talk about a variational quantum algorithm to estimate the geometric measure of entanglement for pure states. So the geometric measure of entanglement for a state psi is a quantity that is given by the distance between psi and its closest separable state. And the distance that we consider here is the infidelity. So this is 1 minus the fidelity between these two states. And we see that if this state is separable, this GME is going to be 0. And if the state is very entangled, this GME is going to be very close to 1. Good. So we see that this is an optimization problem. And we also see that if this state psi is the state of a large number of qubits, we won't be able to calculate the GME because classically at least, because we have to represent this state as a vector, and this consumes an exponentially large classical memory. This is just an like a generic quantum state. Then to solve this problem, we use a variational quantum algorithm. And for that, we define this Hamiltonian H, as we see here, and an ansatz of this form, where this U is a separable unitary, and psi is the state for which we want to calculate the geometric measure of entanglement. So if you do the calculations, you see that this cost function, the expectation value of this Hamiltonian is equal to this infidelity. And then we have our variational algorithm because we have our ansatz, we have our cost function. The circuit now is super simple. We just have to prepare this state psi in a quantum computer, apply a layer of 1 qubit unitaries that are easy to implement because they are 1 qubit rotations and they don't bring too much noise to the problem, and then finally measuring the computational basis. So here
I guess here the computational complexity is in the unitary that creates psi.
Yes.
Okay.
Yes. But you can also think like in I don't know, quantum optics protocol, somebody sends you the state and the only operations that you have to apply are these gates. Right. So and here the estimator of this infidelity is just you get the const you get the const that are associated to the string of all zeros, and you divide by the total number of experiment of shots. So again, prepare psi, apply separable unitaries, and measuring the computational basis to estimate this infidelity. So this is simple. And in principle, this algorithm works, and it gives a good estimation for the GME, and it works for a large number of qubits if you start close enough to the solution. But the issue here is that when you increase the number of qubits and you start the algorithm from a random point in the parameter space, the value of this fidelity decays exponentially with the number of qubits. So it exponentially concentrates around 0. And then we get a barren plateau. So as I was saying, the fidelity concentrates around this quantity, and the estimator of this fidelity is given by the standard deviation of the estimator of the infidelity is given by this quantity. And you want that the standard deviation to be at least of the same order that the quantity that you want to estimate, right? Because you want the error to be smaller than the value of the true value, right? So to have a standard.
What is capital F?
This is this fidelity, like the overlap between these two quantum states, and then a square. Yeah. So if you take two random states in a high dimensional space, this fidelity is going to be for sure this quantity or around this quantity.
So small n is the number of qubits.
Yeah, small n is the number of qubits. Yeah. Yes. So you want a standard deviation. You want the standard deviation of this estimator of the fidelity to be smaller than the fidelity, right? And for that to happen, you need a number of shots, this large n, that is at least of this same value, right? You need an exponential number of shots, and that's why you get a barren plateau in this VQA. Okay, but in our work we saw that starting from a random point leads to a barren plateau. But if we start from a point that is close to the solution, we don't get this barren plateau problem. So what we did is that to replace this global Hamiltonian that we had before with this local Hamiltonian that is a sum of two body terms, and we use the same ansatz as before, a layer of 1 qubit gates applied to the state side. So when we calculate the expectation value of this Hamiltonian over the ansatz with this quantity, and we see that if these rho ij are two-body reduced density matrices that come from this state side, this is in some sort a sum of two-body fidelities with respect to the ansatz, and the ansatz is something separable, so it's a pure state. And now with some calculations, we can notice that the value of this function, this local Hamiltonian, is always an upper bound for the global Hamiltonian, for the value of the GME. So then minimizing this local Hamiltonian takes us closer to the solution of this global probe, to the solution of the GME.
How do you have an idea how the mean value of HL scales with the number of qubits? Because, you know, this bound can be good or bad depending, because, I mean, increasing the number of qubits, let's say the right-hand side of the inequality can be very large. So it would be nice if HL, but no, HL is not suppressed in N. So actually bring, I mean, how HL depends on N. The expectation value of HL.
We just did like numerical simulation, and this quantity was usually smaller than 1. Like this n over 2 times this expectation value of HL was smaller than 1. So because this is smaller than 1, and if you get that this is 10, this is not very useful.
Right.
But this quantity, like at least heuristically doing numerics, was usually smaller than 1.
I see.
Yeah.
Because it's suppressed by 1 over square.
Yeah, and it's also suppressed here, right? So if this is really small, this is also going to be really small. Yeah. Okay, so doing this works and numerically gives good results. But what we tried and worked better was something a bit different. What we did was not optimizing over this full function that depends on all the qubits, but to take a few different terms in this sum at each iteration and optimizing only over those terms. So in particular, we took random partitions of the set of qubits, and we only consider infidelities over these partitions. For example, here we have like the simplest partition for 6 qubits, and we only consider infidelity, this function for qubits 0 and 1, 2 and 3, and 4 and 5. So instead of minimizing this function, we were minimizing these random partitions, and we were changing this random partition at each iteration. And this, you see that these functions are independent. They depend on different parameters. So the minimum of the sum of these three terms is going to be the sum of the minima of each one of these terms. And then we can optimize over these terms separately. So, and we saw that doing this was better than optimizing this full function. Okay, so doing this for some iterations, optimizing over random partitions, bounds in some sense this GME, the geometric measure of entanglement, but we don't get an optimum because the optimum of this quantity is not the same as the optimum of this other quantity. But we get close enough to not to be in the barren plateau anymore. And then in the second step of the algorithm is just optimizing over this global Hamilton. So here's this pseudocode for the algorithm. We start with a random state psi, to which we want to calculate the GME, some number of iterations, and the ansatz in some random parameters. And we have two stages here. So in the first stage, we run the algorithm with the local Hamiltonian. So we choose a number of iteration, and in each iteration, we choose a partition like this, and we optimize over that partition for one iteration. And then at the end, we have some parameters for the ansatz that are closer to the optimum than random parameters in the Hilbert space. And we are hopefully outside of the barren plateau. And then in the second stage, we change to this global Hamiltonian, and we optimize until convergence. So again, in stage one, we optimize this local Hamiltonian, and in stage two, we pass to this global Hamiltonian, but with hopefully we are hopefully outside of the barren plateau, because we are starting closer to the optimum. So finally, here we have some numerical simulations of the protocol. In the first image, we have superpositions of GHZ states and W states of 18 qubits. And as we see in this equation, the blue line here is the exact value of the GME. And the green line is the value that we get with the global cost function. And the orange one is the one that we get with the second VQA, the one that starts with the local and then passes to the global cost function. And well, here we see that the global cost function always stays at the barren plateau. So this value starts at 1 and stays there forever. And the other protocol is much better because you always reach this true GME value.
This you did in absence of noise, right?
Yeah, these are simulations in absence of noise. Only shot noise. You only have we only have shot noise.
Hmm.
And something important here is that we are estimating this gradient using 8,000 shots. So 2 to the 13 shots, and that's why the global function is very noisy and it doesn't converge. Because if we were using 2 to the 20 shots, this curve will probably converge. So the global algorithm will probably converge, but using an exponential number of shots, and we didn't want to do that, right? And finally, here we have some results that we got using IBM's quantum devices. So we prepare a GHZ state of 7 qubits, and we optimize over the global Hamiltonian here on the left, and the local protocol here on the right. So here we see that the 12 curves that the 12 times that the protocol ran in the quantum computer are in a barren plateau. And here on the right, using the local protocol, we saw that at least 6 of them are outside of the barren plateau, and will converge to this green curve eventually with a larger number of iterations.
What is K here?
K is the number of iterations in the protocol, because you are using an optimization algorithm, and this you have to run this optimization algorithm for many iterations. So yeah. Also, one last thing is that the number of shots that we use to estimate or to evaluate the gradients is 2 to the 7 here. So we used a low number of shots because we wanted to simulate, in some sense, the regime of few shots in a high dimensional system.
How many qubits do you have on experiment?
7 qubits. Yeah, and you have a lot of noise, so this is why these curves are not reaching the exact value that should be, right? 0.5.
You say the various curves differ by initial points, by the initial points. I mean, the various curves, they differ in the initialization points.
Yes. So these are different initialization points. Yeah.
I see.
Yeah. So what I can say at the end is that there exists a VQA that can evaluate the geometric measure of entanglement efficiently, as we just saw. Also, we need to be careful and pose the problem that we want to solve in a careful way, because for the same problem we can have a barren plateau or not. Then we also saw that in our specific problem, working with a part of the function that we wanted to optimize instead of the full function was more effective. The convergence was faster, considering the number of shots. And finally, we might be able to extend our results to other problems, optimizing over circuit causal cones separately. So we can optimize in the same way that we did here. We take some terms of the function that depend on different causal cones, and we can optimize each one of these causal cones independently. And that might work better or not. We don't know yet, but we are working on that, and we expect to have results soon. And that was my presentation. Thank you very much for your attention.
Thank you, Leonardo. We have time for some more questions. So maybe let me start. So these 7 qubits that you did simulation, is this kind of the maximum that you could do, or kind of state of the art, or it depends on you?
Yeah, because you need to have access to these IBM quantum devices, and this is the free ones are 7 qubits maximum. Then you have to pay.
Do you know the paid ones? What is the, or is it how much you pay?
You pay a lot. It's like $1 for second or something. And these were like several hours, so it's like it's a lot of money. And I think you can use devices of at least 25 or something like that. And they also have, at least 20 something. 20. Yeah, but probably if we do this in a device of 20 qubits, it won't work, because you need to prepare the GHZ state. And if you want to prepare a GHZ state of 20 qubits, it will probably be super noisy. Like,
Will be not a GHZ state anymore.
Okay.
Yeah, actually, preparing states with high entanglement on quantum computers is still far away. So
yeah. I guess if you want to use 20 qubits, we could prepare a separable state or a product of Bell states or something like that, and then you can prove that and then you calculate something meaningful. I say. But yeah, this is an advantage, right? Because for, I don't know, 20 qubits or 30 qubits, this shouldn't be easy. At least the ansatz is super easy. It's just a layer of 1 qubit universe. It's like the easiest that you could get.
Do we have any other questions? Seems not. So then let us thank Leonardo for this excellent presentation again.
Thank you for the invitation. Yeah.